Say we have a astronomical fix and we are interested in the most probable position. So first have a look in the astronomical position. Say we have a dead reckoning position over here and we have an astronomical fix with a true bearing of 045. That's in more or less this direction. And we have a delta H of 2.5 miles. Then we measure 2.5 miles in the direction of 045, so this is 045, and then we have the first position line over here, so this is a astronomical position line. Then we have, for example, a second line in the bearing 085, which would be somewhere there, 085, and delta H of 3 nautical miles, which could be somewhere there. So we have the second, so this is 3.0 miles. And then a third position line in the bearing 205, which could be somewhere there. Oh, I should have dotted, but never mind. And it has a delta H of -2, so you go this way 2 nautical miles, and then the position line will be something like this. So this is a -2.0. So in this area over here, somewhere in there is your astronomical position. So first make a table with all the measured positions. So we have the line of position number, we have the true bearing, and we have the delta H. So the first lob is 0.45 and a delta H of 2.5 nautical miles. So this is degrees and this is nautical miles. The second one is 0.85, 3 miles. Third one is 205 and 2.0 nautical miles, and the fourth one is a 260 bearing with -4.2 nautical miles. So now we're interested, what is the best position? So you can, as you should do, make a map and make the construction, but you can also use the least square method. So first thing we need is a formula. In this case you could say the x times the sinus of the true bearing plus the y times the cosine of the true bearing minus the delta s, talk about it later, should be something like the delta h. So and the delta is your fixed error, say in this case half a mile. So it's plus, but you have a minus over here. So what we do is we put in all these numbers in the equation. So the first one will be something like the sinus of 45 degrees would be something like 707x added by 0707y minus a half equals, in this case, 2.5. Second equation, it's the second observation, gives the sinus of 85 degrees, which is 0.996x added by 0.087y minus a half equals 3.0, which is this number over here. Third observation, the sinus of 205 is a negative number, 0.423x minus 0.906y minus a half equals minus 2.0. Fourth and last observation, sinus of 260 is a minus 0.985x minus 0.174y minus a half equals minus 4.2. So now we're going to solve these set of solutions, but first thing we do is making a matrix of it. and it's quite straightforward. We just take here the 0.707, then the second one is 0.707, it's the I value, and I have minus a half. I multiply this with x, y, and the delta sigma, the error, and this should be 2.5 and the rest of all the numbers. So completing the matrix, this should be a 0.996, 0.087 and minus a half. You can do this in decimals as well. 0.423 minus 0.906 and minus a half if you like, and minus 0.985 minus 0.174 and minus a half. Well, this is a 3.0 minus 2.0 minus 4.2. So this gives me the matrix A times a vector x is a vector b, and I should be able to solve this. Well, I need some space over here. See if I can move the screen a little bit, something like that. Yes. So because this is a 4 rows 3 column matrix, it has no inverted. So what we do is we make a square matrix by AT times A times X is AT times B. So what I put on the left side I should do on the right side as well. So this should go because I'm interested in the X value. So I take the AT times A invert AT times A times X. So if do the inverse on the left side, should it here as well, AT times A minus 1 and AT times B. This, no matter what's in here, as long as the inside is the same, gives the unit matrix times X is the same thing. So for matrix multiplication you can consider this I as a number 1. Depending on the matrix size, this is a 1, 0, 0, 1 or whatever. So we're now able to calculate the X using a calculator. There are dozens of screencasts explaining how to do that for your specific calculator, so I skipped that part. I'm interested in the X value. So what I found out is in my calculator the X value is something like 3.642, 0216 and a 0858. Immediately store this one as another in my part C matrix, because we're going to use that later on. So what's the implication of this all? Well, say if you have a this is your dead reckoning position. So we can say we go at 3.6 miles to the east, and we have a 0.2 miles to the north. So this is not in scale, 0.216. So somewhere here should be your position. Interesting. So we're quite able to, without the construction of the astronomical position line, which is fun, but we can do without. So so you can put these to your dead reckoning position and you get your position. So position is 1. I would like to know what's the error. Well, if we look at the equation, which was somewhere here, then you can also imagine that there's always an error involved. So here is something like error 1, we have an error 2, etc. So because the measurements are not accurate, so what we get is here I have A times X minus the error equals something like the B, or this could be added, maybe that's easier. So if I want to know the error, make it in green, I take the B factor minus AX, and the X is the thing I just calculated, because that's the position difference. Okay, interesting. So put this in my calculator. I got something like an E factor of, say, 0.201 minus 0.218, 0.168, and minus 0.147. So these numbers are interesting because they are the errors for your respective lob numbers. So the error of lob number, line of position number 1, line of position number 2, etc. So you can see what your specific errors were in taking your astronomical navigation fixes. Well, back to what we were trying to do. We were taking a astronomical position. So normally we do it the old school with all the constructions, but we found out that with a least square method, it's also possible to calculate the whole thing. Well, I hope this was an instructive video, and see you next time.